Hello and welcome back to Calculus 1. This is section 4.9 on antiderivatives, also known as integrals. And we are going to talk about this its operator, right? This mathematical creature from the derivative point of view, and then we'll define some other stuff when we move to chapter 5, like the other approach. Derivative of x squared is 2x. So the antiderivative of 2x should be x squared, because you are supposed to go back to the original function. So the way we write that is we write this squiggly line, then we put 2x inside and we put dx at the end, and then we say it's going to be x squared. Make sure you have some room after x squared by the end of the, to the end of the page. What I have to do is I have to add stuff here eventually. Why? Because what is the derivative of x squared plus 10? 2x. So what was the integral of 2x dx before? It was x squared, right?
Yeah, but you can't determine the constant, right?
Exactly, right? You already see the issue. The derivative destroys this constant. So when you want to undo the derivative which produced 2x, there is no way for you to retrieve 0 or 10 or negative 9. So that's why we put this plus c to emphasize that there's supposed to be some unknown constant there that we don't have at the moment. We don't have a way of determining. Right? It's what it is. Now, before we move on, I want to mention that in mathematics you have the world of operations, which are addition, subtraction, multiplication, division, squaring, and so on. And the world of operations changes numbers. And then you have the world of operators. And those would be limit, derivative, and integral. What they do is they change functions. Now, obviously, these are not exhaustive lists. These are just examples. There is much more to both of these lists than what I wrote. So when you have mathematical operation between two numbers, 3 plus 5, plus is mathematical operation, and 3 plus 5 is 8. So we change 3 and 5 into 8. 3 minus 5, negative 2. 3 times 5, 15. So we are changing these numbers of 3 and 5 into 15 and negative 2 and 8 and so on. Observe what the derivative did. Derivative changed x squared function into 2x according to the rules of differentiation. The integral is going to undo that from changing 2x back into x squared, and then we have to put this plus c because we really can't determine this constant by just integration. We have to do more work. We'll see that later. So technically, do you know integration already? The answer is yes, if you know your derivatives well already. Because I can ask you, what is the derivative of sine x? And you would say cosine x. So now, what is the integral of cosine x dx? It will just be sine x plus c. This plus c is not there for decoration. You always have to have it. So technically, if I know my entire derivative chart, I know my entire integral chart. So now if I ask immediately, what is the integral of 1 over x dx? You would say, what thing, you always have plus c, derivative of what thing in this box would give result of 1 over x? ln x. See that? And then we'll have to put the absolute values here, but so you always start, you can always start by saying what should go in a box so that this is the answer if I differentiate it. Integral of 3x squared dx is equal to what? So what should go into the box? X cubed. Very good. Because derivative of x cubed, you drop 3 down, and then x 3 minus 1 is 2. So that's exactly what we have there. So that's one of the way to deal with integration. What thing would give me the sign in the integral, right? Now, it's important to understand that this and this are a pair. Okay? They always go in pair. Because, well, there are many reasons. The first thing you learn is that since we are only doing mechanics of the calculation, not the theory, the theoretical part is that this is actually the width of the rectangle you're computing for area, but that's maybe later today, we'll see. Right now, please remember that your notation for the derivatives was to put d dx in front, right? And you would read this, take the derivative in respect to x of x squared. So each one of these things in the notation had its importance. Instruction to take the derivative, instruction to take the derivative in respect to x in particular, and then giving you the function inside, what are you taking the derivative of. So that was very, very specific. So now, and why is that important? Because I can have this, d dx of mx plus b, right? So it's very important to know what the independent variable is, because this problem is completely different if I have this. We know that from our chain rule section or implicit section, whatever. The variable, independent variable, matters. So for derivatives, right, it was always clear what is the function and what are you taking the derivative in respect to. So now for integrals, that is encoded here. You are taking the integral in respect to value x, right? Because, guys, this gets upgraded, right? Let's go. Calc 3. It gets upgraded. dy, dz, dx, right? You have to figure out which one you need.
So,
do you see this? This over here is actually a Calculus 1 integral. The box inside. You see that the dy, but you have two different variables. The first one would be a constant. And when we integrate it later, which is going to be later in this class, right, you are actually going to know how to do this today, even though there are certain aspects of this that look scary, but it's not that bad. So you guys have to just understand the notation first, and the notation is if you have multiple variables, let's say you had the y as well over here, anything else other than what d provides, everything else is a constant immediately. So can we take the integral of ax dx? And the answer is yes. This a is a constant, so we copy that, and then we will have x squared over 2 plus c. Because the notation for integrals is, this is the instruction, which is integrate the antiderivative, and this part tells you what is the main variable that you are focusing on and worrying about. Yes?
So, like theoretically with the integration, you should be able to be given a tangent line and define the function of that tangent line is tangent to.
Yes. So you're going backwards. So this is going backwards. Very good. What else do we have? Well, we have some formulas. Integral of a constant a dx is just going to be ax plus c. So what's integral of 7? What's integral of 7?
So would that be like the reverse of the 7th derivative?
No, it's just integral of 7.
Oh,
Integral of 7 dx. It will be?
7x plus c.
Very good. 7x plus c. Because to check the derivative of 7x plus c, the derivative of 7x is 7, plus derivative of c is 0, and there is a 7. You can check using the derivative. So the derivative of a constant is that. Integral of x to the n dx. This is integral of x squared, integral of x to the 5. But also all of the integrals of square roots and cube roots and 1 over x cubed, everything is in here. I'll do 3 examples. Is x to the n plus 1 divided by n plus 1 plus c. Right? We know that for derivatives you subtract 1. Well, it should be common sense that for integrals you add 1 because you're going the other way. So the examples in this category. Integral of x to the 9 dx would be x to the 10 divided by 10 plus c. You can take the derivative to check. 10 would drop down and cancel denominator, and you just have x to the 9. So it's good. How about integral of 1 over x to the 6 dx? So see, when x is in denominator. Well, you first rewrite this as x to the minus 6 dx, and then we have, you're adding 1, so x to the negative 5 over negative 5 plus c. So there is that answer. And finally, let's say you want the 6th root of x to the 5, whatever, dx. Not a problem. Use algebra to rewrite this as x to the 5 over 6 dx, and then just again add 1. So if you have x to the exponent, it doesn't have to be positive integer. It could be negative integer, it could be a fraction, it could be anything. Your job is to say it's going to be plus 1. So x to the 5 over 6 plus 1 divided by 5 over 6 plus 1 plus c. And then you just clear these fractions, make it nicer. So this is x to the 11 over 6 divided by 11 over 6 plus c, which turns into 6 over 11 x to the 11 over 6 plus c. If you simplify, right, the double fraction, you bring it up, it flips. So that one rule takes care of a lot of stuff for us. So the next few rules: integral of e to the ax dx, you know, like e to the 3x, e to the 5x, is going to be e to the ax divided by a. Right? So for derivatives, a was on top. For integrals, it's on the bottom. It's opposite. So integral of e to the 3x dx is 1/3 e to the 3x plus c. You see, always you have this plus c, plus c, plus c. It's always there. We already talked about this one. Integral of 1 over x dx, which is ln absolute x plus c. We have to toss in the absolute value now. It's not there for decoration. And the reason for it is the domain. So absolute value added because of domain. And if you think about this, right, 1 over x graphs this way, so your domain is from negative infinity to 0, union 0 to infinity. That's the domain of the function. So you are allowed to plug in on the left side positive and negative numbers. The only number you're not allowed to plug in is 0 on the left-hand side. Now, on the right-hand side, if you don't have absolute value, you only have this for ln, and that's a problem. But if you put in absolute value, it's going to go like that. And then we have the same domain. So that's the reason why we have to have this absolute value. And you know, students usually complain, oh, but I just forgot this absolute value. Well, yeah, you forgot the half of that function to put in. And then that creates a problem, because if you need to plug in -7 on this side, because you don't have negative values allowed, if you don't have absolute values, you can't plug -7 on the right, which breaks the equal sign and breaks the entire formula. So absolute value is not there for decoration. It needs to be there. Now, there are no examples for this, because that's it. You know, it's just a single case. If you ever see 1 over x, it's ln absolute x. There's no numbers that we can change. All of the trig ones, integral of sine x dx is close, negative cosine. Because what is the derivative of cosine? It's negative sine, right? So that negative has to play there. What is the integral of cosine x dx?
Wait, I'm sorry. Can you repeat that again?
About the cosine here? The derivative of cosine alone is negative sine. And then you will have extra negative to kill that negative. Because now integral of cosine is just sine, x plus c. So they're opposite, right, with sines. So you have to think a little bit. Now, do we have the derivative of tangent? Integral of tangent? We don't have it actually as a basic integral. We are supposed to undo the derivative ones. So what are the answers for all the derivative for trig? Well, one of them was secant squared x dx. So this is a basic integral that produces tangent x on the other side. Integral of cosecant squared x dx, which produces negative cotangent x plus c. Integral of secant x tangent x dx is equal to secant squared x plus c. And integral of cosecant x cotangent x dx is equal to negative cosecant, oh, it's not squared, just cosecant x plus c. It's not squared, it's just basic one. Now, if you are to look at your derivatives of trig functions, you will see, derivatives of trig functions, you will find all of these written backwards. You will find that the derivative of secant is secant tangent. We can actually jump into the section of trig derivatives. There we go. And when you jump to that, what do you get? There it is. The derivative of secant is secant tangent, which means that the integral of secant tangent is just secant. Are we learning any new formulas? No. No. We're not learning anything new. We are learning how to read everything we know backwards. So we can go back. Now, let's do this in blue, I guess. If any of the trig functions if any of the trig functions has ax, let's say you have integral of sine ax dx, then this ax is going to run in front. Then you will still have your cosine x plus cosine ax plus c. Or let's say you have integral of cosecant squared ax dx. That would just be negative 1 over a cotangent ax plus c. So this a in front of x is going to jump in front as 1 over a, and then whether you have a positive or negative there, right, that will still be the same. So what is the integral of secant 3x tangent 3x dx? What is this equal to? So what is the integral of secant tangent? So 1/3 secant 3x plus c. So whatever the value is here, it goes as 1 over, right, on the outside, because the formula is 1 over a. Which would mean that integral of, let's say, cosine of x over 2 dx would be 2 sine x over 2 plus c. So it always switches the side of the division line. What happened? Integral of cosine is sine.
No, the one before, the secant 3x tangent 4x, 1/3 secant 3x.
Plus c, yes. Because the formula is 1 over a. And if the formula is 1 over a, and your a is 3, then it becomes 1/3. But if your a is 1/2, when it goes up, it becomes 2 over 1, which is 2. So that's why over here is 2. Because the input was half rather than 2x. Like 2x would go into 1/2, x over 2 would go into 2. It's always opposite. Because the formula is 1 over. So it flips.
I guess my question before was what happened to the tangent, though? It was
The derivative of secant is secant tangent, which means that the integral of secant tangent is secant. That's what the where is my? I'm trying to find here. There it is, right? When you're going back, you get a single, right? Because remember, integrals and derivatives, they are changing functions. So they change functions. They change sine into cosine. They change secant tangent to secant, right? Depending on whether you have derivative or integral.
yeah, because for some reason I kept putting it as secant x squared, or secant squared x.
Yeah. Is there anything else? That's pretty much it for the intro. And now we're going to talk about some properties and things that you can do with this stuff. But basically, you have to think derivatives backwards. And it's called antiderivatives. So now for properties, we have this really cool thing, which is that the integral of f of x plus g of x dx is equal to integral of f of x dx plus integral of g of x dx. So they're independent, right? If you have functions, and I'm going to add subtraction as well in the same formula. In the book there are two separate formulas, but so if you have addition or subtraction, you take the derivative of each one independently. It's not derivative, integral. It's really cool because you can have x squared plus e to the 6x dx. So the rule allows you to look at this as two separate functions. And that's awesome because they're both basic functions and we can quickly come up with the integration. So x cubed over 3, right? Because it's plus 1 over n plus 1. Plus, from the form over there, and you have now 1 over 6 e to the 6x, and then plus c at the end. So the 1 over 6 is because it was e to the 6x, right? That 1 over a is the same rule for sine, cosine, and e. So all of this stuff works that way. Independent derivatives. Now, your book would ask you for things like this. What is the integral of cube root of x plus 1 over x minus cosine x dx. So what is this equal to? Try that one. So if I know that I can rewrite this cube root as x to the 1/3, right? So we are immediately adding 1, so that's x to the 4/3, right? Over 4/3 plus ln absolute x minus sine x, because derivative of cosine is positive sine, so the sign doesn't change, plus c.
For the middle one, can you do x to the -1? Can you do it that way?
Yeah, but when you add 1, you will get x to the 0 over 0. You see why it doesn't work, right?
I got you. Okay, yeah, I messed that up.
But the ln is there to save the day. Good. One more property rule, and this one is for the constant. If you have a constant times a function, dx, you can kick constant outside of the integral, just like for derivatives. You kick the constant out. It's for limits. You kick the constant out. So integration has the same deal. Kick the constant out and just focus on working with the function. So what is the integral of 6x cubed dx? Well, by the rule up there is immediately 6 integral of x cubed dx. Right? That's immediately what it is. And then you can just focus on integrating x cubed. You don't have to worry about 6 because you get to copy 6. Integral of x cubed is?
X to the 4th over...
Yes. Because the formula for x to the n, right, the formula for x to the n is always xn plus 1 over n plus 1 plus c. So 3 plus 1 is 4. So x to the 4 divided by 3 plus 1, which is 4. So x to the 4 over 4. One more time to repeat exam 3 on chapter 4, scheduled for 8, Saturday 8. So that's 3 Saturdays from now, or 2 Saturdays from now, whatever. Next time is a review session from chapter 2, 3, 4. Bring in your exams if you have questions on any of the problems, exam 1, exam 2. We are trying to be very efficient in preparation for the final, that it's here in 4 weeks. On the 15th is the final. So we have class on the 1st to finish up the lectures, class on the 8th to have exam and 3-hour review, and then 15th is the final from 9 to 11, and the course is over. Right? That's it. So it's very, very quick. Now I'm going to put some problems directly from the book. We covered what we were supposed to cover. You have the basic integration formulas where you use backwards derivatives to deal with what you get on the other end. And you have the properties that if you have multiple functions separated by plus and minus signs, you can do each one individually. And then the rule for constant, that you don't have to worry about constant. You just kick it out, deal with the function as is, and just multiply constant back. So here are some examples from the textbook. And, you know, some of these exercises are very interesting. So, because these exercises are geared that way to kind of bait you into making a mistake, right? For instance, I'll give it a little bit simpler example. X squared times 3x cubed minus x dx. You really need to start this problem because it has a very dangerous trap in it, and that's that x squared in front. See, you can't integrate this straightforward because it has multiplication in it. You know how for derivatives you had to learn product rule, right? You had to learn product rule, right? Well, integration has its own forms of product rule called use substitution, integration by parts, and other things that you will also learn in Calc 2. So the way to do this is to distribute x squared, and then you can integrate. Because you don't know any of the forms of product rules, and there are multiple ones. And most of them are in Calc 2. You don't know the rules of product rules for integrals to solve this. So your only bet over here is to distribute x squared, and then you will have subtraction of two functions, and those can be done independently, right, one from another. So we're all good, right, in that case. And pretty much all of the problems, and I think you have about 60 of them, 60 given in a book to practice of this type. All of them are rewrite them using basic algebra so that you only have basic functions to deal with. And you have to do long division, you have to do distributing, you have to do canceling, factoring and canceling, like all of these things across the board so that you can solve the integral. So for 4.9 now, you should be asking yourself immediately not what integration technique to use, because that should be always clear. You are supposed to ask yourself, what algebra do I get to perform to get this into basic functions? So now we have multiplication of these. As soon as I multiply, what do I get? I get 3x to the 5 minus x cubed dx. That's what I get. And now these are basic functions. You copy 3 out, and then you just have x to the 5, integral of x to the 5, that's easy. And then you have integral of x to the 3. So this is further equal to, kick 3 outside, we have x to the 6 over 6 minus x to the 4 over 4 for a total of 1/2 x to the 6 minus 1/4 x to the 4 plus c. Plus c is important for every So they give you, this is problem 37. Integral x squared minus 36 over x minus 6 dx. You immediately see what you're supposed to do, right? So what do we do? Factor. Good. So we have x minus 6, x plus 6, divided by x minus 6. Cancel. And all I have to worry about is x plus 6 dx, which is x squared over 2 plus 6x plus c. And that's that. I know how much you love trigs, so we can't skip that one. Sine theta minus 1 divided by cosine squared theta d theta. Now you can use x dx, t dt. Yeah. We're using theta d theta now. All right. $1 million question, huh?
I'm trying to get this magna for the entire semester. I'm trying to get this magna for the entire semester.
Probably a new video.
Whatever this thing is, just... I have no grip on it.
You have to slide like a piece of sheet metal, like thin slice underneath it.
Yeah. Safe. Oh, I haven't tried that thing.
Let me put your feet.
There's a hole. I'm determined. I have 3 more classes to figure out because I always forget. And then when I see it, I'm like, oh yeah, I still have this project going on. It's not done tomorrow.
Is it ceramic on the top side? It's a ceramic. It's probably a ceramic gate.
Got it. I'll figure out how. I couldn't use this.
Sorry.
No problem then. No problem then.
Yeah.
So, when you look at this problem, we have 2 terms in numerator. and a single term in denominator, which means that you can split this into two fractions and then use trig identities to write the simplified versions. So I'm going to now split this into sine theta over cosine squared theta minus 1 over cosine squared theta d theta. These big parentheses are important, and you will see that importance shortly, because we are going to define integral very shortly as length times the width. And then if you have a times there, obviously that times wants to multiply into each one, not just the last one. So we'll talk about those details soon. When I work this out, I have sine theta times 1. This one gets its own cosine and the other one gets its own cosine, minus 1 over cosine square, well, I can do that, 1 over cosine theta, everything squared, d theta. And now, what's sine over cosine? And what's 1 over cosine? Secant, right? 1 over cosine is secant, so minus secant squared theta. And as you can see, now we have basic ones to deal with. The integral of secant tangent is secant theta minus integral of secant squared is tangent theta plus c. That was problem 46. They give you about 6, 7, 8, 9, 10, 12. I have about 15-ish of these trig ones. Here's another cool one, 49. This would be a good conversation starter now for the Black Friday holiday thing that's going on. Very good. So you already said it. We distribute secant. We get secant theta tangent theta plus secant squared theta plus secant theta cosine theta d theta. What are we going to do for the secant theta cosine theta? What's secant? Yeah. So what's secant? 1 over cosine. So how much is 1 over cosine times cosine? 1. So the whole thing is just 1. Great. So we have integral of secant theta tangent theta plus secant squared theta plus 1 d theta. So secant tangent, the integral of that is secant theta, plus secant squared is tangent theta. And what's integral of 1?
X.
Yeah, in this case theta, right? Plus c. Yes. And there we go. Done deal. In case you're not sure why the integral of 1 dx is equal to x, here is why. You can write 1 as x to the 0, right? Can you?
Mm-hmm.
So x to the 0 plus 1 over 0 plus 1 is x to the 1 over 1, which is x plus c. Yay. So integral of 1 is x. Integral of 2 is 2x. Integral of 3 is 3x. I think we had 7 as an example. Integral of 7 is 7x plus c. The last part of this lecture, and then we go hit the break, is the way to compute c, the meaning of c, and all of these kind of things. So when I have, so constant, let's talk about constant c, constant plus c, right? So if we go back to what I had earlier, talking about the derivative of x squared being 2x, the derivative of x squared plus 1 being 2x, the derivative of x squared minus 1 being 2x, and then combining all of this into integral of 2x dx equals to x squared plus c, we know what this plus c does to functions from pre-calc 1. What does it do? Graphically.
It moves it to the left and right?
It moves it not left and right,
Down.
up and down. So I have my x squared, then I have my x squared through 1, then I have my x squared through negative 1. You see that? These are graphed there. You see that there is a plus c that will tell you there are infinitely many of these all stacked on top of each other. All of these x squares. And they're stacked forever. Now, if I pick a point, say right here, if I pick a point, that point belongs only to that graph. So in order for me to calculate the c, to pinpoint which of the infinitely many lines is the one that we're looking for, I would have to have that point, and we call that initial condition. So, initial condition. Point given to us to determine value of c. So let's take a look at an example. Find c for integral of x cubed minus 3x squared plus 6 dx given point 1 4. Well, we have to integrate. We know how to integrate because all we need to do is do what we did before. 1 by 1. X to the 5 over 5. Sorry, supposed to say x cubed. X to the 4 over 4 minus x cubed, because over 3 would cancel 3 there, plus 6x plus c. And now I have, so now all of this is equal to y, right? Equal to f of x. All of this is equal to f of x. I use capital F of x for antiderivatives. And I know that's all equal to 4 when x equals 1. So I have my equation. 1/4 minus 1. Well, actually, let me write everything out. So 1 to the 4th over 4, I'm plugging in, minus 1 cubed plus 6 times 1 plus c is equal to 4. And as you can see, c is the only unknown that I need to compute. 1/4 minus 1 plus 6 plus c equals to 4. This is 5, move to the other side, so c is equal to 4 minus 5 minus 1/4 equals to negative 5/4. So negative 1 minus 1/4 is, you can either put negative 1 and 1/4, or you can just do negative 5/4. So the answer is that the antiderivative is equal to x to the 4 over 4 minus x cubed plus 6x minus 5/4. And this is the particular line that we are interested in, because we had initial condition to compute the exact c that we need, and we were able to retrieve the information that derivative destroyed, right, when derivative was taken. So I want to, okay, here is problem 80 for you to practice, and we are done with this one. It says integral of 1 plus 6 sine t dt, and the point is given as age of pi over 3 is equal to negative 3. Integrate, plug in pi over 3 equal to negative 3, and compute the value.